How does an electron fall to the ground state? Let's discover the fascinating decay path. In this problem, 11.16, an electron in the n equals 3 state and L equals 0, M equals 0 state of hydrogen decays by a sequence of electric dipole transitions to the ground state. Part A. What decay routes are open to it? Specify them in the following way. 300 to some other level in LM, some other level in prime L prime all the way to the ground state. Part B, if you had a bottle full of atoms in this state, what fraction of them would decay with each route? And then C, what is the lifetime of this state? Okay, now this one is kind of tricky because what we're really asking for is how long does it stay in the 300 state and then get to the first transition. So, why do we care? Well, this is an application of the selection rules that we've been yapping about for the past 3 problems and even back in chapter 6. So we'll see how nice this is. And then the challenge for you is what makes the electric dipole needed? Now, if you've taken electricity and magnetism, you'll see why it's important, but here we see it is playing a pivotal role over and over again. That being said, there's a lot of work in this, so you might want the PDF that has all the words and extra algebra stuff. Comment if you want it, and I'll send it your way, or you can access it with the Patreon link in the description. And before we jump into today's topic, I want you to know that I break these things down piece by piece using exercises from these top books. So if you have a book you want to recommend covering next, please do. I'd love to see it. I'm thinking classical mechanics, but if that sounds of something that's interesting to you, please join us in that exploration and subscribe to the channel. But without further ado, let's jump into this. All right, so straight to stop number one. All right, let's get a general feel of the landscape. If the electron is in the state NLM equals 300, okay, that means that we're going to decay to something lower. Okay, that's what decay means. We go from a higher energy level to a lower energy level. And in such case, we could go to 2 with all the L and M combinations, and eventually to the ground state. To determine which transitions are allowed, we can reference the selection rules from equation 11.75 and 11.76. Okay, and then from there we can, begin to see what the paths are actually going to do. So let's begin by listing out all possible paths from the 300 state, and then run through the selection rules. So as you see, I'm 300 all down. I could run straight to the ground state. I could run straight to 200 or 210 or 21 plus or minus 1. Okay, but now we see that the selection rules come in, given by 11.5. Okay, so here our delta L here is the state we're going to minus the state we're in. Okay, so if this is, let me get the pen out. If this is referenced as N, L, and M, okay, this 0 comes from this, and this 0 comes from this. Okay, so from there, we see that we need to be 1 in order to transition. Okay, because that were the selection rules based on angular momentum conservation and things that we saw back in chapter 6. That being said, because we have a 0 minus 0 equals 0, this transition cannot be allowed. So we can't go from the n equal 3 state to the n equal 1 state. Similarly, we can't jump to the n equals 3 to the n equal 2 state either. Okay, but we see that every other one is allowed. So clearly, we're going to have to go from 300 to 21 and some number. And then here, if we check the selection rules from the M perspective, right, we see that we need to be 0 or plus or minus 1. Those are the only allowed states based on equation 11.75, but we also showed that with some of the selection rules back in chapter 6. So here's a great application. So since we have x's there, we can't use those 2 transitions, but we can use the last 3. That being said, this summary overview tells us that the only path the electron can or is allowed to take from the n equal 3 level is to the L equal 1 position in the n equal 2 level. But from this point, the electron can still decay. So let's check these paths. So now we have to go from the 2, 1 level with m equals 0 plus or minus 1 to the ground level. So our L's, they're all negative 1, so we're fine. And then the M's, they're all 0 or plus or minus 1, so we're fine. So that's good to go. That being said, we need to summarize these paths, right? And so summarizing them in the form that the question gave us was 300 to something with the 2-1 state, and then M being a selection there, all the way to the ground state. Okay, so that's pretty cool. And again, the two things to note here is that the 300 to 100 and the 300 to the 200 violate the delta L equal plus or minus 1 rule. And this is summarized very neatly here in the visualization of the past from 11.9. Okay, so we see that we're starting here, n equals 3, L equals 0, and we have to transition. We see that this arrow tells us we have to go to the L equal 1 state for the n equal 2 level. And then that's when we can go to the n equal 1 state. That's pretty cool how you can create this just based on geometry in the arguments that you have from the wave function. That is pretty fascinating. I don't know how they came up with this in the middle of the early 1900s, but that's very, very fascinating. Okay, so now that we know what paths to take, now we can move on to stop 2, okay? And in this case, what we're tasked with doing is finding the probability of each path, and sometimes this is called the decay mode. So this part focuses on the various decay modes via electric dipole transition, via the electric dipole radiation. So to determine the fraction of a specific transition, in this case, which route, we need to calculate the squared magnitude of the electric dipole, as described by equation 11.51. And from problem 11.13, we know that the position vector is a vector operator and with its own selection rules that we again revisited in problem 11.14. And this is summarized all in the equation 11.76. So to minimize the number of integrals that we need to evaluate, let's begin by identifying which matrix elements are 0. Okay, so we know that from 300 to 210, the electric dipole is state, state, and then the position vector. So knowing that the position vector is just x I hat, y j hat, z k hat between the two states, we can just split them up into the vector. And now we see that x here, y here, z there. We know that from equation 11.76, the first one in it, if m prime equals m, we know that the x and y inner products go to 0. So immediately we save ourselves 2 integrals. Okay, beautiful. Then going from the 300 to the 2-1 plus or minus 1 state, again doing the same split up here, we see that m prime equals plus or minus 1. So this 0 plus this, we're good. And that's pretty darn cool, right? And so since that holds there, we know that we can use 11.76 part 2, in which case we know that the relationship between the x inner product is related to the y inner product with an I. In this case, since we have plus or minus 1, we have plus or minus I. So now we reduce from 2 integrals here. Oh, and by the way, the z1 is 0, as you can kind of see the green there. So what we see is that we reduced 2 inner products in just this line to 1 because we referenced it with the y at the cost of an I. That's pretty darn awesome. And then the z goes to 0, so we got rid of so many matrix elements here just by doing that one thing. Okay, and then when we factor this out, the plus or minus I will go on the I hat. So that's why we have that there. And then we have plus j hat because it's still a vector. These are scalars, so we're good. And so based on the 3 transition states we have from 300 to the n equal 2 state, that would have been 9 possible triple integrals to be found. When really what we show is that we only need 2. And that saves us a whole host of time, which you will see very shortly why. So before we can actually find the inner products, what we need to do is define our wave functions from these states. So given that the ket there is 300, that's the wave function of 300 for the hydrogen atom, which we know is composed of the radial part and the angular part. So referencing the tables in the book, I think 4.3 and 4.7, we can go ahead and clean this up and find our wave functions. Here is the 300 wave function. Here is the 2-1 plus or minus 1 wave function, and here's the 2-1-0 wave function. Okay, lots and lots to clean up, so be very, very careful whenever we approach this, okay? And I'm purposely putting things to half powers because we know that in the inner product, we're going to have the conjugate times the other wave function, so we'll have squares appearing everywhere, all right? And so from now that we have all our wave functions defined, we need to take the inner products that we found in the last slide where we were able to decide what inner products were actually needed, or matrix elements. But before we do that, what do you think about this as a theory, its applications? Drop a comment below with your thoughts. I love hearing your interpretations and questions. That will inevitably make it all better for the learning community as we get more feedback. All right, so from the 300 to the 210 state, the only inner product left was the Z1, okay? And so we need 𝜓₃₀₀ with the conjugate, Z, 𝜓₃₀₀ dV, okay? We know here that Z, however, is equal to R cosine theta. So we have to plug that in into spherical coordinates. And when we do that, we get this whole host of mess. Again, most of it's in the PDF step by step, but as you see here, there's a lot of cleanup left, so we're going to have to do that. Once we clean it up, get all the constants outside, things like that, apply U sub here because we have R over A everywhere. So if U is equal to R over A, R is equal to AU, dr is equal to ADU, and then, of course, the limits here, same as you'd expect. Upon doing that, what we see is that after substituting in, we get this R4 goes to A4, U4, so A4, A4 cancel. That was the Bohr radius. dr goes to ADU, so we have an A there. So we'll have one Bohr radius left over. Cool, don't care about that. But right now, what we see is that we also have the phi integral and the theta integral, split them up accordingly. And then we could see that after substituting and simplifying, this A goes out front here. We can actually clean this up pretty quick, meaning that we distribute this u to the fourth into these parentheses here. So we have all of that, as well as the exponential, double distribute. Okay, phi integral goes to 2 pi, theta integral goes to 2/3, so 2 and 2, that's a 4, that reduces this 324 to an 81, pi and pi cancel, and then we have this 3 that's just going to be multiplied in, that's easy. Now here we see that we have exponential integrals with some outside factor. Instead of doing integration by parts 1,000 times, this is in the book as a table integral, so just use that. The power here tells you how many factorial you need, as well as then you need n plus 1. So just put that in there. And then you have to divide by the whatever's multiplying by u. So that's 6 over 5 everywhere. We see we have a lot of 6 over 5s here. So eventually we're going to have to clean this up, as well as these coefficients out front. So get ready for algebra. Okay, as promised, here we go. We see that we have 6 to the 5th power over 5 to the 5th power times that 4 factorial, 5 factorial, 6 factorial. So 4, 5, 6. And then we see that we have all these powers. This is the 6 to the 5 plus 1 since it was raised to the 6th. 6 to the 5 plus 2 since it was raised to the 7th. And then when doing this, we highlight that we can bring the 6 to the 5th, 5 to the 5th outside. If you're really, nitpicky about it, you could just plug it into Mathematica, let it simplify down. Most of the time, though, you don't have that on tests, exams, projects, things like that, and they want to see how you handle the numerics. So I would get used to just having algebra. Once you have that factored out, then this becomes just a simplification. Just find a common fraction here. That's simplified to 648 over 5. And from that, you can just simplify down as much as possible. This 5 joins this 5 here, so hence 5 plus 1. 234 gets put into the fraction now when you do that. That reduces down to a 8 over 3. Note here that this 6 is 2 times 3, and that's all to the 5th power. The reason why we want to do that is because we have 2 to the 5th times 3 to the 5th over 5 to the 6th. We see we have a 6 there, so that'll inevitably be done the same. But because 8 is 2/3, we can combine the 2's, and because this 3, since we're dividing by 3, we can cancel this 3 up here. So ultimately, we end up with a over root 6, 2 to the 8th, 3 to the 4th, 5 to the 6th. Numbers that are a pain in the butt to deal with, but at least we have them in a compact form. There's a whole lot of running around. Mathematica could probably simplify it pretty quick for you, but sometimes we're just looking at what the actual number is versus the size of it in expanded form like Mathematica would give you. So keep that in mind, and eventually you'll see it cancels out kind of nice. So enough of that. We have to rinse and repeat this whole process, except now with the 2, 1 plus or minus 1 state. Here though, because we have the exponential in it, we're going to have this flip because of the conjugate. So instead of plus minus, it's minus plus. And then that green, we're going to have to break up into the phi integral, which we'll see next up. Constants outside, split everything up, and we'll rinse and repeat. Okay, same u sub, rinse, repeat. But now we see that on the phi integral, instead of just having sine phi from the wave function, or d phi, oh, I forgot my d phi, sorry. We split that exponential up via Euler's identity, so we have this. Cool. We see that after the substitution here, the 𝜓₃₀₀ cancel again. Perfect. We distribute the sign here. This theta integral goes to 4/3, so that 4 will reduce the 648 to a 162. We distribute again on both sides, so now we just have the same rinse repeat process with the exponential integral. Easy enough. Now this sine, cosine, that leads to 0. And then we have I sine squared, so that leads to I pi. Okay, phi integral simplifies, fair enough. All that 3 gets multiplied there. And then we're just going to use the same tactic of simplifying this radial integral here. 6 to the 5th everywhere, factor it out, clean it up. You see that the I here now takes its stronghold up top with the A from right here. And now we just clean it up. Same thing, rinse, repeat, clean, and summarize. So, again, clean, summarize, just bullet it all down. What you see here is that you end up with IA over root 3 instead of root 6. Then you have 2 to the 7th instead of 2 to the 8th, 3 to the 4th, 5 to the 6th, things like that. Okay. So now that the integrals are complete, which is arguably the hardest part about this, we need to get back to the electric dipole. The electric dipole was defined in 11.51, but we see here that from the transition from 3 to 2, 1, 0, we have Q with the radial inner product, or the position vector inner product. And we saw that since we only had a z hat left, or the z component left, which is k hat, we just put Q and then this in the k hat direction. Cool. Now here we have to be careful finding the square magnitude here, because we have to square everything. So that root 6 goes to 6. We multiply 2 everything else, as you see, color coded, simplify down. 6 goes to 2 times 3, so we can simplify up here. And ultimately, we're left with q squared a squared, 2 to the 15th, 3 to the 7th, 5 to the 12th. Okay, this is still more compact than the number that would have been seen in the mathematical expansion. So that's why we like to keep it like that, especially when comparing other large numbers. Now here, we have to be utterly careful with the transition from n equals 3 to the 2, 1 plus or minus 1 state, because we actually had 2 components. We had the I hat and the J hat, okay? Thank you, selection rules. So here, we have to clean this up and get the I's and the plus or minuses tidied up however we can. So let's do that. Distribute this I into these components. We see that we get minus plus staying outside. We'll just keep all that nice and tidy. And then we see that we get plus or minus I squared. And then that I squared turns to a -1. So we flip that minus plus there. Now when we distribute this minus plus into the vector coordinates, or vector directions, we have minus minus, that gives you plus, plus plus, that gives you plus, but this plus just takes on the minus plus. Okay, so now that we have that simplified, let's go ahead and square it and see how it compares to this number. So squared everything, that cube or square root of 3 goes to 3. You multiply by 2 to everything else, since, squares, we like that. But, and the thing with finding the magnitudes is you had to take the square root of each component squared, but since you're squaring it, that square root goes away, so you just have this times this, and then again, with the complex nature, we have the conjugate multiplied by the thing itself, so that plus or minus I got flipped, and then we multiply by negative plus. As you see, positive to negative is negative, negative to positive is negative, so regardless, we end up with the negative there, but it's I squared. That I squared goes to -1. That -1 and negative there turn to a positive 2, so eventually we get the other 2 that we want, that we were missing last time. But we notice that q squared, a squared, 2 to the 15th, 3 to the 7th, 5 to the 12th, that's the exact same number that you had from the other state. So since all 3 of these states have the same number, what this tells us is that the transition rate for all 3 are the same number, And since they are the same number, the fraction that goes each route is exactly 1/3. That's pretty darn cool. Okay, so we radiate to each path equally. Okay, and who would ever thought that from the onset here with all these large numbers and all this chaos going on with these selection rules? That's pretty insightful, and I really like how that played out. But with that, we're now done with part B, and now we need to find the lifetime in part C. Okay, so now in the lifetime, we know that to leave the n=3 state, all we have to do is get to the n=2 state, and then the state no longer exists. So for the lifetime of the n=3 state, we can just look at what is the transition or spontaneous transition in lifetime from the n=3 to n=2. Okay, and so that was pretty much the hint provided in the question. And similar to problem 1 or 11.13, we can set this up using equation 11.63. Okay, and that we'll see how this all comes. Since we already calculated the electric dipole in part B, by applying the formula, we can express 𝜔₀ in terms of E1 in order to have this simplified and easier numerical calculation. And since the charge here is just an electron, we know that Q equals E. And so let's go ahead and start plugging these in and simplifying. All right, so finding omega here, which we know we need for the spontaneous emission rate, we see that that's going to be E3 minus E2 because we're transitioning from the n=3 to n=2 state. Clearly use the Bohr formulas here, which was back in chapter 4. So E1 over 3 squared, E1 over 2 squared, simplify that common denominator. Now we see here, keep an eye on this 36 because 36 is 4 times 9. And we could break 4 down into 2 squared and 9 down into 3 squared. We saw we had 2 and 9s or 2 and 3s earlier, so that'll be useful to you, as well as 5. And then when we're talking about the lifetime here, because we can go 3 different routes to get n=3 to n=2, but all routes are even probability. Route 1, Route 2, Route 3, spontaneous emission rates for each of these routes. Since they're all equal, we just put a 3 there. And now when we want to look at the spontaneous emission rate, which is from 11.6, we see that we have the 𝜔₀ and the electric dipole squared. Thankfully, we found both of them already. So we see that plugging these in, the 3 and 3 cancel here. Cool. We're dividing by a fraction, so multiply by the reciprocal. That gives you pi epsilon naught h bar c cubed, omega cubed, and the electric dipole squared. In the magnitude, of course. Okay, so the total lifetime, make a note of each decay mode, is this formula. Now we just have to plug everything in. Okay, so omega cubed, we did the splitting up of the 36 into 2 squared and 3 squared like we had mentioned, or like I had mentioned. I don't know. There's a lot of people who talk about this problem. Anyways, then we see that the magnitude of the electric dipole squared came out to be the same number. And again, since we had 2, 3, and 5, it was just easier to do that. So go ahead, get this cube, put all the 3's in their respective spots, and multiply accordingly. We see that Q is equal to E, so that turns to an E squared. Okay, now it's just a whole lot of simplifying and substitution to get you in the proper position to evaluate the numbers. Okay, so with the h cube here being in the denominator of a fraction in the denominator goes up top, so that's why you have a plus 3 up there. This 2 to the 6 and this 2 to the 15, there's a minus. 3 to the 6th, 3 to the 7th there, minus. This 5 is up top, this 5 is below, so we need to minus them. Because ultimately that 5 belongs in the numerator, so that's why, the big numerator. And then what we're going to do is split this negative E1 cubed up into E squared and negative E1. We'll see why in just a second, but it all come full circle. Here we're going to substitute in to get some things canceled via the Bohr radius and the energy state there. So h bar squared here cancels with that. 2 and this 2 to the 9th will simplify down. A squared and a squared cancel there. So this ME will also go up top. Note that we finally put this 5 to the 9th from here up top as well. So get ready for a lot of weird substitutions to simplify. All right, so after that, we clean it up, we simplify our h bar, get everything simplified down. We have ME and E1 squared. Now what we have to do is put things together like the pi epsilon h bar squared and e squared here to substitute in the Bohr radius. And why we do this is because what we're trying to do is put ME and C squared together for the substitution with the electron volts. So get rid of that, simplifies that down. A comes back in, we have ME over 4, but 4 is just 2 squared. So we see that 2 to the 8th gets a plus 2 now. We have our A there, ME gets a square now, and we're good. But in order to write this in terms of squares, we need to multiply by C over C, so that C to the third, C cubed can go to C to the fourth. And then we see that that's just MEC squared, so the energy there. But since we're trying to make a big thing squared here, we need a C to the fourth, so that's why we multiply by C over C. And then we see we just have some numbers chilling outside. That's exactly what we wanted. Again, since we want this in seconds, but we know that the energy was measured in electron volts, we use the mass speed of light principle here from Einstein, and we're good. Now we can plug in all our constants. Okay, color-coded, of course. We see this is the conversion, so we're good. Square that. We see that we end up with something really, really tiny. So then go ahead and put that in sig figs. We see that we get a lifetime here of 1.58 times 10 to the negative 7 seconds. So that lasts just under or just over a millionth of a second. That is very, 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 very crazy. All right. That was a long video, but I found it very important to look at and discuss the application with the theory, not just talk about the rambling of the theory. So if you like this video, please subscribe. It was a blast to make. And, thank you for all the support for the Patrons. And, as always, keep that curiosity high and keep learning because we need more learning now than ever.